Welcome to Network Theory Lab. And in this video, we are going to conduct another experiment. And the objective of our experiment is to design a first order passive low pass filter and to obtain its frequency response. So here we can see this is the first order passive low pass filter circuit that consists of one resistor in series with one capacitor. So normally in this case, when we are having the first order low pass filter, in such cases, the input will be applying between these two terminal. Here you can see in this particular figure. So this is our V input. So V input will be applied between these two terminal, and the output will be taken across the capacitor. So here we can calculate what will be the transfer function of the circuit. So normally we have to first take the Laplace transform for each of the elements and also for your output and input variables. Okay. So if we do that, we will be able to show that this transfer function HS is normally given by this expression 1 upon 1 plus RCS. So in any low pass filter or any filter, we normally interested about the what will be the 3 dB cutoff frequency of the filter. So you will find that this 3 dB cutoff frequency of first order low pass filter is normally given by this expression f equals to 1 upon 2 pi r into c. So this is our 3 dB frequency expression. So this is our designing expression for the filter. So normally when we are designing any filter, we must know what should be the 3 dB cutoff frequency, right? So based on that, we can choose our element values. So suppose if you wish to make the first order low pass filter, then you must think about, because it is a passive low pass filter, so obviously and there will be no gain offered by the circuit. So maximum gain that you can get is equals to unity. Okay. So while designing, you must know what should be the values of R and C should be taken. Okay. And that will be decided by what will be the 3 dB cutoff frequency of the filter. Right. So normally to design the low pass filter, we have to follow this particular expression because 3 dB cutoff frequency is given by this expression. So what we can do is, because if f is known, right, in that case, we have to find out what will be the values of R and C. So let us suppose that if we wish to make a low pass filter with 3 dB cutoff frequency equals to 1 kilohertz, in that time, this f will become 1 kilohertz, and then we have to find out what will be the values of R and C. So in such cases, what we can do is we can choose one of the component. So let us suppose if I choose this capacitor value equals to 10 nanofarad, and if we put f equals to 1 kilohertz, then obviously we will be able to calculate the value of resistance, right? So if you do this simple calculation, just you take this f equals to 1 kilohertz, you design this filter for 3 dB cutoff frequency equals to 1 kilohertz, and this you just choose this capacitor value equals to 10 nanofarad, then you will be able to calculate this value of resistance R. Okay, so that calculation, a simple calculation, I have already done, and I have made this particular circuit. So here you can see this capacitor value I have taken equals to 10 nanofarad. And if you do this calculation, simple calculation, then you will be finding that this resistance value should be equals to 15.9 kilo ohms. Okay, to get the 3 dB cutoff frequency equals to 1 kilohertz, right? So here is the simple circuitry experimental setup that you have to make to get the frequency response. So you see this observation table, right? This observation table we have to obtain. So here we have to take the sinusoidal wave as the input. Okay, we have to apply the sinusoidal wave as the input, and obviously because it is a passive circuit, okay, output is also going to be a sinusoidal wave, right? But obviously its magnitude and phase may be a little bit different, right? So here you can see to apply this input signal as a sinusoidal wave, I have taken the function generator, and here you can see this function generator, I have selected the here input signal as equals to sinusoidal wave, right? So we have to apply the sinusoidal wave, so you can select only sinusoidal wave. So here I have to select this one, and then we have to also fix its peak to peak amplitude. So you see, normally while conducting this experiment, we have to get this observation table. In this, the first column is corresponding to the applied frequency. The second column is corresponding to the input signal peak to peak value. Okay, it's amplitude, right? So it is the peak to peak amplitude of your input signal. And then we have to measure the peak to peak amplitude of our output signal. And then we have to calculate the gain. And this gain will obviously, it will be V output divided by V input. So that way we have to calculate the gain. So you remember that when we are keeping this peak to peak value equals to 1, this calculation becomes very easier, because whatever we are measuring from the output, whatever be the output peak to peak value, that peak to peak value will directly become the gain, right? So that calculation becomes easier, and that's why normally you can keep this input peak to peak value equals to 1 volt, right? So that I have kept here, and then we have to calculate this absolute gain, which will be V output upon V input. And then we have to calculate the gain in dB to get the plot of frequency response curve. So here you can just see how to conduct this experiment. So first we have to take the sinusoidal wave of 50 hertz, right? So just let me go to this multisim software. So here you can see we are having the function generator, and here we have to make it 50 hertz, right? So let me make it 50, and this should be in hertz, right? So here you can see this amplitude, right? V maximum is equals to 0.5 volt. Okay. So why we have kept it 0.5 volt? Because V peak to peak will become 1 volt, right? So that we can verify from this CRO only. Okay. So if you execute this circuit, right? After executing, here you can see onto this channel B, our input signal is connected. Okay. Here you can observe that. Okay. This channel B, our input signal is connected, and it will be coming in white color, right? So first we have to properly adjust our time sensitivity and amplitude sensitivity to observe this signal, right? So let me adjust this time sensitivity according to applied frequency, right? So here I have adjusted this value, and let me adjust this amplitude sensitivity also, right? So here I'm just making this amplitude sensitivity equals to 500 millivolt, right? So at this time here you can see that this both the waveforms are almost overlapping, the input waveform and the output waveform, right? So here, because I'm only interested in the input waveform right now, just to ensure that the signal is of 1 volt peak to peak signal, and whatever the frequency that I have applied, like 50 hertz, it should be a 50 hertz signal, right? So let me do one change in the circuit. Okay, so let me just disconnect this one for a time being. Okay, so I'm not connecting the output. Okay, I'm just connecting the input, and I'm just measuring this input signal, right? So just to make sure that only input signal is coming over here, now I can stop it and you can do this measurement, right? So simply we can measure it from this waveform itself, right? So here you can see this amplitude. Okay, channel B amplitude sensitivity. So channel B amplitude sensitivity, here you can see it is 500 millivolt per division, right? So here you can see this value. So it is right now I have set this value up to 500 millivolt per division. So here you can see, because this is our amplitude sensitivity. This is our amplitude, right? So in this section, in the vertical section. So here you can see this waveform is actually covering two vertical sections. So this is corresponding to 0.5 volt or 500 millivolt, and this is corresponding to another 500 millivolt. So altogether, you can see this V peak to peak value for the input signal is 1 volt. So this is what we have set in our function generator, right? So I will keeping this value constant throughout our experiment. I will not change amplitude, right? Another thing that we can ensure is about our frequency, right? So that frequency I have set equals to 50 hertz, so that you can calculate what will be the time period. So time period, obviously it will be going to be 1 upon 50. So that you can ensure here, right? So that you can see also from this curve. Okay, so if you keep it at the bottom, right? So this is our T2, and another pointer you can keep it at this point. Okay, so here you can see this at the bottom, you can see this time difference, right? So T2 minus T1 here, you can see it is coming out as 19.793 millisecond. So if you correctly set this value, we will be getting this value equals to 20 millisecond, which is equals to 1 upon 50 hertz, right? So obviously we will be able to generate the same signal, okay? Whatever I have generated out, whatever the setting I have done here for the function generator. So this way you can first ensure your input, right? Now, because only in the input case, we have to change the frequencies and we have to keep on measuring the output amplitude, right? So what I will do now is you can just disconnect this signal because it is not required, okay? We are not going to measure the input because we are interested only in the output signal, right? So you just make this connection here, okay, in the function generator, and now we can run this circuit, right? So once you will be running this circuit here, you can again measure, because in the channel A, the amplitude sensitivity is 500 millivolt per division, okay? So again, what we can do, you can stop it here and then you can see how many divisions it is covering, right? And this way you can again do this measurement and you can note down these values into the observation table, right? So right now it is coming out as 1 volt peak to peak, right? So here this value is coming out as 1 volt peak to peak, so that you can measure from this graph itself, right? And you can see this amplitude sensitivity, or otherwise you can also bring this pointer to this maximum point, okay? T2 minus T1, again you can see, so this is at the maximum point and then it should be at the minimum point, right? So here you can see this T2 minus T1 time is okay, but here you can see at the channel, this amplitude, the difference of the amplitude is coming as 0.994 volt, okay? So you can correctly, you can set, you just make a little bit adjustment, you will find that this value will be coming around 1 volt, okay? So it is approximately around 1 volt, right? So that value I have already noted down here, okay, in this observation table. So here in normally in this multisim software, we have another facility, right? Either you can do measurement by using this way, okay? You can use this CRO, you can observe the waveform and you can keep on changing this sensitivity wherever it is required, or you can do this measurement, right? Or otherwise, I can also have this particular voltage probe, which is available in the multisim software only, right? So that probe we can also connect over here, okay? And if you execute this, you will be able to see this V peak to peak value. So this V peak to peak value here, it is coming out as 0.997 volt, right? So almost 1 volt. So I have written here, it is equals to 1 volt. Now you can change this frequency 100 hertz. So first you have to stop it, okay? And then you have to make it 100 hertz. So once you will making it 100 hertz, right? If you execute this again, you can see there is a little bit difference, a little bit decrease in the amplitude of output signal is observed. It is 0.994, okay? So this value I have noted down here, it is 0.994, okay, 0.994. So you see this input V peak to peak signal, I have not changed, only V output peak to peak signal is changing, right? So again, you can make it 200 hertz, 300 hertz, 400 hertz, 500 hertz, and so on, right? So I will be showing you this data for corresponding to 500 hertz. So if you stop it and if you take this 500 hertz, okay, so just make this value equals to 500 hertz, then again you can observe this changes, right? So if we execute here, you can see this V peak to peak signal is coming out as 0.892 millivolt. So that you can decrease in the amplitude, you can observe here again, okay? So this changes, you can see, because I have changed the frequency up to 500 hertz. Again, we have to adjust the time sensitivity, okay? So we have to adjust the time sensitivity, and now you can simply observe this waveform, right? Now this waveform is not touching this top horizontal line and bottom horizontal line, okay? Because the signal amplitude has decreased now, right? And that proper measurement you can again make by bringing these pointers, and then you can see the differences in channel A, right? So if you do that, you will be able to observe that this T2 minus T1 in channel A, it is coming around 0.88 volt, right? So that value exactly you can see from this voltage probe, okay? So that voltage probe is showing this value equals to 0.892. So that I have noted down here for this 500 hertz input signal. Okay, so it is 0.892. So this way you can keep measuring all these outputs for frequency 600, 700, 800, and 900 hertz. Okay, and you have to measure this value up to 5 kilohertz signal. Okay, so I will be showing you this particular data. If we make this input signal input frequency, okay, of equals to 1 kilohertz, then you can see this signal again, right? So if you make it 1 kilohertz, here you can see this V peak to peak is coming out 0.705. So that I have also noted down here. So this way you try to perform this experiment, and you will find that as we are increasing the input frequency of the signal, this V output peak to peak amplitude is going to be decreased. Okay, so this value is decreasing, right? It is decreasing linearly. Okay, so here you can see when we are having 5 kilohertz signal, that time this amplitude is decreased to 0.195 volt. Okay, so this way you can do this observation, right? So after completing this observation table, you have to calculate the gain. Okay, and as I said that initially, that because this V input peak to peak is equals to 1, whatever observation we are making in this column, the same thing will become the gain. Okay, and to get the your frequency response curve, normally we have to calculate the gain in dB, and normally to get this gain in dB, you have to apply this formula 20 into log 10, and we have to take this absolute value. Okay, so this way you have to calculate the gain for your entire rows. So this way you can calculate the gain in dB, right? So this way you have to complete this table, right? And one thing that we can observe from the graph itself is this observation itself is that the maximum gain that we were getting is around 1 volt. Okay, maximum gain is around 1 at this point. And normally we know that at 3 dB cutoff frequency, normally what happens is this maximum gain, the gain of the low pass filter will become 70% of its maximum gain. So here you can see this is 1, and its 70% is coming around this point. Okay, 0.705. So it is now 1 upon root 2 times of the maximum possible gain of the filter, right? So at this point, even you can see this gain in dB. So normally at this point, gain in dB is 0, and now it has been reduced by it is reduced by 3 dB. So that's why this point is normally called as 3 dB cutoff frequency, right? So here we have to plot this curve. Okay, we have to plot this frequency response. To plot this frequency response, normally you have to use the semi-log paper. Okay, onto the semi-log paper you can plot this curve. But here in the Excel sheet, we can select this particular column, and then you have to press the control button, and then again you have to select this frequency column. And here we have this facility. You have to go to the insert tab, and then here you can go to the charts, and you can select this option. Okay, scattered with smooth lines and markers. So this will be giving you this particular chart, this particular plot. Okay, and then we have to just change this particular frequency scale. Okay, so here onto the frequency scale, you just double click, and then this format axis tab will open, and here we have to make it logarithmic scale. So once you will make this logarithmic scale, you will be able to see that this low pass filter frequency response, right? So normally you have to use this semi-log sheet. Okay, you remember that this magnitude axis will be on to your linear scale, but normally the frequency axis will be in the logarithmic scale. So that's why it is normally called as the semi-log paper, right? So here you can see in between this two line, the frequencies covered is 1 to 10 hertz. But in between this two line, it is 10 to 100 hertz. Okay, and here you can again see between this line and this line, 100 hertz to 1 kilohertz. So here you can see it is not a linear scale, right? It is a non-linear scale, right? So that's why normally it is called a semi-log paper, right? So this way you can obtain your low pass frequency response. So one thing that I would like to mention here is that if suppose if you are not comfortable with the measuring with the CRO. Okay, so you can conduct a similar experiment by using the multimeter, right? So how to conduct that experiment? So normally you must have the multimeter in your laboratory. So you can take the multimeter, okay, and then you can measure the voltage, right? You can measure the AC voltage. Fine. So just you connect this multimeter in your circuit, and then you can try to measure what is the voltage across your capacitor. So once you will do this measurement, you remember that here you are going to get the values in the RMS form. Okay, this will be your VRMS value. So from the VRMS value, you can calculate your V peak value. So we know that the VRMS is equals to V peak divided by √2. So normally to calculate the V peak, you can multiply it with the you can calculate if it is giving you the VRMS value, then obviously to calculate the V peak, you can multiply it with your √2 value. Okay, so that way you will be able to calculate the values, right? Or even you can note down the VRMS values. Okay, doesn't matter because the factor will be a common factor. So again, you can make this type of observation table, and then you can calculate the gain, and then you can plot the frequency response, right? So I hope you must be able to conduct this experiment. So if you have any query, let me know with your comments, and stay connected with the channel for more updates. So thank you for watching this video.